Ever wondered what makes elements react differently? It's all about the valence electrons. Absolutely, you got it correct. These subatomic entities, referred to as valence electrons, are the often underappreciated heroes of the fascinating world of chemistry. They dwell in the extreme outer layer or shell of an atom and have a pivotal role in deciding how an element behaves chemically. Now let's use a metaphor to better understand this concept. Picture atoms as microcosmic solar systems. Similar to how planets revolve around the sun, our solar system, electrons in an atom orbit the central nucleus in layers, which are referred to as electron shells. And it's the outermost of these shells where the real action occurs. The quantity of valence electrons in this outer shell greatly influences how an element will interact and react with other elements. Some elements are quite generous and are always ready to share their valence electrons with others, while there are also some that are more inclined to borrow electrons from. This exchange or sharing of valence electrons forms the fundamental basis of all chemical reactions. Whether it's the rusting of iron, a common oxidation process we see around us, or the burning of hydrogen, a simple combustion reaction, at their core they are nothing but the result of the interaction and interplay of these valence electrons. So to have a clearer understanding of the world around us, to answer questions about why and how different substances react the way they do, it all down to understanding one thing: valence electrons. So the key to understanding chemical reactions lies in the valence electrons. Now that we know about valence electrons, let's dive into how they form bonds, specifically ionic and covalent bonds. Think of atoms as social butterflies. They love to interact, and they do so by forming bonds. First up, we have ionic bonds. They're a bit like a game of pass the parcel, where electrons are the parcel. In this game, one atom donates an electron to another. This transfer creates ions, atoms with a positive or negative charge. For example, when a sodium atom loses an electron to a chlorine atom, it forms a sodium ion and a chloride ion. These ions attract each other, and voila, we have an ionic bond. Now what about covalent bonds? This is where atoms decide to share instead of transfer. Like good friends sharing a pizza, they distribute the slices of electrons evenly. Oxygen molecules are the perfect example. Each oxygen atom shares 2 electrons, forming a double covalent bond. This sharing of electrons allows them to fill up their outermost shells, achieving a stable state. Here's an easy way to remember. Ionic bonds involve a transfer of electrons, creating charged ions that attract each other. In contrast, covalent bonds involve the sharing of electrons, helping atoms achieve stability together. But it's not always a clear-cut case of ionic or covalent. Some bonds can have both ionic and covalent characteristics. It's a spectrum, not a binary. For instance, a bond might be mostly covalent but have a tiny bit of ionic character, or vice versa. But that's a topic for another time. For now, just remember this: atoms bond to achieve stability. In ionic bonds, they do this by transferring electrons and forming ions. In covalent bonds, they share electrons. The way they bond depends on the specific elements involved. Remember, in ionic bonds, electrons are transferred, while in covalent bonds, they are shared. Ever heard of bond parameters or Lewis structures? They help us understand these bonds better. Let's start with bond parameters. These are properties that help us describe the nature of a chemical bond. 3 main parameters come to mind: bond length, bond angle, and bond energy. Bond length, as you might guess, is the distance between the centers of 2 bonded atoms. It's measured in picometers. Bond angle, on the other hand, is the angle formed by 2 bonds that originate from a common atom. It's measured in degrees. And lastly, bond energy is the energy required to break a bond. It's typically expressed in kilojoules per mole. Now let's talk about Lewis structures. These diagrams are a simple way to show the arrangement of valence electrons around atoms in a molecule. The Lewis structure for water, for example, would show 2 hydrogen atoms bonded to 1 oxygen atom, with 2 lone pairs of electrons on the oxygen atom. To draw a Lewis structure, we first need to count the total number of valence electrons in a molecule. Then we arrange the atoms, usually placing the least electronegative atom in the center. We draw single bonds between atoms, and then distribute the remaining electrons as lone pairs. It's important to remember that each bond represents 2 electrons, and that each atom in the molecule should have a full octet, except for hydrogen, which only requires 2 electrons to be stable. So when we look at a Lewis structure, we're getting a snapshot of how the electrons are arranged in a molecule. This helps us predict how that molecule will behave in chemical reactions and also gives us insights into its physical properties. So, bond parameters and Lewis structures give us a clearer picture of what's happening within our molecules. Let's delve deeper into the world of bonds with polar and covalent character, valence bond theory, and resonance. Starting with the polar character of covalent bonds, it's important to note that not all covalent bonds are created equal. In some cases, one atom might be more electronegative or electron-loving than the other. This means it will pull the shared electrons closer to itself, creating a slight negative charge. The less electronegative atom ends up with a slight positive charge. This uneven distribution of charge is what we call the polar character of a covalent bond. On the flip side, we have the covalent character of ionic bonds. Ionic bonds generally form between metals and nonmetals, with the metal giving up one or more electrons to the nonmetal. However, when the ions are in a polar environment, like water, the ionic bond can take on some covalent character. The ions share their electrons more than they would in a pure ionic bond, and this sharing is what gives the bond its covalent character. Now, let's move on to valence bond theory. This theory tells us that a chemical bond forms when the atomic orbitals of two atoms overlap and share electrons. The greater the overlap, the stronger the bond. This theory helps explain why atoms form bonds in the first place and how the structure of a molecule relates to its function. Last but not least, we come to resonance. Some molecules can't be accurately represented by a single Lewis structure. Instead, they exist as a blend of several structures, each contributing to the overall properties of the molecule. This phenomenon, known as resonance, is a testament to the flexibility and complexity of chemical bonds. These concepts add more layers to our understanding of chemical bonds. Now we can appreciate the intricate dance of atoms and electrons that gives rise to the incredible diversity of substances in our universe. We've covered a lot today. From valence electrons to resonance, we've journeyed through the world of chemical bonds. We've seen how valence electrons play a crucial role in the formation of bonds and how the transfer or sharing of these electrons leads to ionic or covalent bonds, respectively. We've delved into bond parameters and the Lewis structure, enhancing our understanding of the structure and characteristics of molecules. We've also explored the polar character of covalent bonds, the covalent character of ionic bonds, and the valence bond theory. Moreover, we've understood the concept of resonance and its significance in chemistry. Remember, chemistry is all around us, and these concepts are fundamental to understanding the world at a molecular level. So keep revising and applying them to different chemical reactions. Thank you for joining us on this journey. If you found this video helpful, please like, share, and subscribe to our channel, Facts Academy 0122. Don't forget to leave your comments below. Until next time, keep exploring the world of chemistry.